Hello students, welcome back. Let's resume section 4. As a matter of fact, I wanted to complete section 4 in a single video, but I failed. The primary reason, right here, I spent quite a bit of time proving these two, and that's because the algebraic manipulation part was not difficult, but the setup was, and I spent quite a bit of time setting up the problem and repeating. But I think that was time well spent, and let's complete the rest of the topic, and we're going to go over to matrix computation with computer algebra system. Okay, the next topic is similar matrices. One of a big use of inverse matrix is this one. We say two square matrices A and B are said to be similar if there is an invertible matrix T for transition matrix as a matter of fact, such that T inverse AT is equal to B. If so, then it turns out A to the nth power and B to the nth power are also similar. And here's a sketch of proof. Here nth power means repeated multiplication. What do you mean B to the nth power? This is B, isn't it? So take the nth power, which means repeat multiplying n times. First batch, second batch, third and fourth, and all the way to the nth batch, repeated multiplication. And here we apply the associativity. The associative law says we can switch the position of all these parentheses so we can take the T and T inverse together, these two together. And that becomes identity I. And there's T, and then another T inverse there, another there, and then this last one, T inverse, and the T was before that. And all the I's there will be cancelled out because those are just identity. Multiplying identity just doesn't change anything. So the middle part is just repeating multiplication of A n times. What do you get? A to the nth power. So the result is B to the nth power is equal to T inverse A to the nth power times T. So yes, A and B are similar, then any power are similar to each other. Final topic. How do you find out an inverse matrix? Well, we talked about the inverse matrices and we talked about some theory behind it. We talked about the inverse rule here, especially this one. Yes, that's really important. But then again, how do we actually calculate the inverse matrix for given matrix, given invertible matrix? Or how do I tell whether a matrix is invertible or not? Well, for 2 by 2, you can use this formula. For higher dimensional case, it's going to be harder. For example, if you have something like 5 by 5 matrix and you know it's invertible and you want to find out its inverse, it's going to take hours to do that. And of course, right after completing all this, we are going to start computer algebra system. So that's where we're going to do some inverse computation and of course a lot of other matrix computation too. But for 2 by 2, you should know, and 2 by 2 is really simple. So some computation like 2 by 2, 2 by 3, up to about 3 by 3, you should be able to do without help of any computer. So here it is, and then let's prove it. Just brute force computation. You see A, B, C, D, and then you just multiply the candidate of the inverse function to your left. And then let's see, 1 over AD minus BC, let's keep this fraction, and then we just do this matrix multiplication, this times that. So basically, first row, first column, times first row, second column, and then just repeat it. And what do you end up with? This is what you end up with, just brute force computation. And BD minus BD, AC minus AC cancel each other out. Here we have AD minus BC, AD minus BC, and divide by this AD minus BC. Then you get 1, 0, 0, 1, identity matrix. This quantity AD minus BC is called a determinant. And That's gonna be an important topic in chapter 7 of this textbook. Well, for example, what is the example? Okay, find the inverse of the given matrix, if any, and then let me cook up some matrix, 2 by 2 matrix. Let's see, A is, let's see, copy and paste this one, and then shall I -1, 2, 6, and then 3. Okay, as good as any. Okay, I just cooked up a problem. Okay, and let's do this. For simplicity, I kept all these as integers. Alright, what is A inverse? 1 over AD minus BC, so -1 times 3 minus BC, 2 times 6. Okay, and then the matrix, I have to switch the order of principal diagonal, so this becomes 3, -1, and then the other, just keep them with opposite sign. Oops. Okay, this is gonna be the inverse matrix. Let's simplify it just a little bit. How about this fraction? This is -3, and then 2 times 6, that's 12, minus 12. -3 minus 12, I'm getting -15. And there you go. That's the inverse matrix. If you want to pass on this 1 over 15 inside and then get a little bit different form, go ahead. It's okay. And if you think there are too many negatives flying around, then I can pass on this negative inside and then change all the signs. Okay, let me stop here. This is the inverse computation done by traditional paper and pencil method. And then let's see. Let's cook up another problem. Four, 2, and then 5. No, let's see. 10. Okay, all right. And let's find out inverse of this matrix. Okay. 1 over, and then multiply the principal diagonal, right? 4 times 5 minus, and then the other 2 times 10. And then how about the matrix part? We have to switch the principal diagonal and then put negatives to the others. Basically, that's what this formula says. And then let's simplify. But what do you get? 1 over 20 minus 20, and looks like this is no good. As a matter of fact, the answer is undefined. Yeah, let me write like this. B is not invertible. That's the answer. You see, you cannot have 0 in denominator, but you did. So this whole formula broke down. As a matter of fact, yes, indeed, this will be a non-invertible example. Okay, all right, let's keep those and then save as. Okay, I just added one more problem, but I may have to polish a little bit. So instead of just saving as a new notebook, but a temp file, and then I'm going to do some editing later on. Okay, all right. We went through inverse matrices, and then we went through a bunch of other things here. But then again, matrix multiplication and matrix inversion, those are really time-consuming computation in general. So how do you effectively do those using computer algebra system? Let's answer the question. Let's go to matrix multiplication example. And okay, here's an example problem as good as any. And then let's open up a new Mathematica. Oops, what did I do? Okay, all right. New window. And then let's do some work here. I'm going to give you some commands. Okay. How do I define matrix? Let's clear some variable. A, B, okay, all right. I'm going to define A. Let me use bigger font. And how am I going to define a matrix? Let me define this matrix. Mathematica is structured like this. Parenthesis for order of operation. These arrays are all braces. Brace open. And then that's for big outside, these. And then we need another brace for a row vector. And then 1, 0, 1, negative 2, row. And then the next row, 0, 1, 1, negative 3. And then the third row, negative 2, 0, 0, 1. And that's how I represent matrix in Mathematica. Brace open and brace row, brace row, brace row, and then brace close. That's a matrix expression. I'll ask Mathematica to enter this, and then it just entered. However, oh, I forgot comma here. Okay, all right. Okay, that looks good. But then again, it's a little bit difficult to see what this really is. So here's a useful command. Matrix form. Matrix form. And then represent this A in matrix form. And ask Mathematica to show it in matrix form. And I have traditional expression. Now, does it really look like this? Of course. Now, I want to see this, not this one, which is a little bit hard to read. So let me enter, but without showing. Let's put semicolon in there. And if you have done some programming like Java or anything, you'd know all about semicolons. Here in Mathematica, usually another function is added, and that function is doing the operation, doing something, but without actually showing. Now, how about the other matrix? This one. Brace open for big parenthesis outside, and then first row, second row, third row, and that's my B. I can enter, but this one doesn't really look good, so let's do that, but without actually showing anything. Semicolon, and then show me the matrix form. And does it look like this? That's how you program Mathematica. This is really elementary program, but this is how you do it. Let's see. If you use Wolfram Alpha, you can't do this. Everything has to be done on a single line because that's a free version. But every registered UNT students can get Mathematica for free and installed. So please go ahead and do that. For most of the mathematics majors, it's going to be useful. It's free. Talk to appropriate people in IT help desk. They'll help you. All right, matrix multiplication. How do I multiply matrix? If I multiply A times B, and that's not going to be helpful. The proper notation is A dot B. Why? Because dot is for the dot product, the scalar product. And then as you recall, matrix multiplication uses scalar multiplication, scalar product, the dot product, and it's an extension of dot product. So using A dot B for matrix multiplication. If you do that, you're going to get the matrix, final answer, but then again, whether this is right matrix or not, -7, 1, 8, -8, 1, 2, 3, looks like it's correct, but it's a little bit hard to see. So I'll ask Mathematica to show it in matrix form, and that's what I got. That's the answer. So A, B, and this is A times B. Some other example? Okay, all right. It's always a good idea to clear the variable before starting anything. And then let me see. Let me copy and paste this thing. So this is 3 by 4 matrices. There are 3 rows. Let me just add one more row. -6, 1, 3. Okay, all right. And then show me the matrix form. Okay, now I have a square matrix. It's a 4 by 4 matrix. So same as this matrix that we started off with, but I inserted one more row down here and made it into a square matrix. Now that I have a square matrix, maybe I can consider the inverse matrix, if the inverse exists. Well, how do I find the inverse matrix of this 4 by 4 matrix? If you use paper and pencil method, it's going to take maybe an hour. Maybe not that bad, but it's going to be pretty bad. So I'll ask Mathematica to do it. Matrix form, this is X, excuse me, and inverse, and that's gonna give me the inverse matrix. This will ask me, this command here, inverse of A, and that asks Mathematica to calculate the inverse matrix, but not just that, calculate it and show me in matrix form, not those single line form. So this will give me the answer. And here we go. This is what Mathematica spat out, and this is, as a matter of fact, the inverse matrix. Well, let's see. Let's call it like this. Clear both A and B. And let's name B as the inverse matrix, and then show me B. Okay. So far, I didn't really change anything. So A is this, B is inverse of A, and if I just calculate inverse, then it'll spit out like this. It's a little bit hard to read, so show me in matrix form. That's what this last line did. And now, show me A times B. Now, am I going to get the identity matrix? A times inverse of A, that should be identity. Am I going to get identity? Let's see. I did. So that's how you do some elementary computation with Mathematica. We'll do more as we encounter more and more topics. But for now, this is going to be a good exercise for Mathematica.